时间好像差不多了，然后我们就正。
Okay, let's begin this afternoon session. So this session is a session concerning cloud native and edge computing, and I welcome all of you. Let's begin today's session. I'm the first speaker. I'm Xu Fei from Huawei Cloud. I mainly work on CubeEdge community. Today, I'm going to talk about KubeEdge, the cloud-native edge computing platform. This is my self-introduction. I'm a KubeEdge maintainer. I used to work in K8s and Istio community. I co-authored a book called Native Service Mesh Istio. I'm now focusing on cloud native and edge computing. Today, I talk about edge computing platform built on cloud native, the advantages and challenges. Second, I talk about the overview, architecture, and core capabilities of KubeEdge projects concerning how we use cloud-native capability on edge computing. Number 3, I'll talk about application scenarios. And lastly, given that KubeEdge is an open source community, so I'll talk about the introduction, future prospects, and the follow-up plans for the community. First of all, here I listed some major challenges faced by edge computing. First, I think the interoperability is poor due to numerous segments of edge computing. Second, edge cloud communication networks feature low quality and high latency. Often the connection is unstable, and the network quality is low and latency is high, and often the edge is located on a private network. Number 3, edge resources are limited, especially in some campuses or production lines. Small boxes are used. CPU and memory are very limited. Number 4, the edge is offline. For example, in campus scenario or in connected car scenario, the edge is often offline. So how to ensure the service is not interrupted when the edge is offline? How to make sure the application can run smoothly? And this is another challenge that we need to tackle. Next one would be how to effectively manage the highly scattered edge nodes and reduce O&M cost. Next, the last one is about how to leverage heterogeneous resources. Traditionally, we have a lot of software and hardware coupled together. Sometimes, if you want to change hardware, you also need to change software. So based on all these challenges, when you think about how to leverage cloud native to address these challenges, these are the core advantages of cloud native. First, cloud native decouples software development for higher flexibility and maintainability. There is a thing called container images. We only need to have one image. Then, as long as this container is supported, then this can be run in all the places. So this is one advantage. Second, we can avoid intrusive customization. K8s has good extendability. Its APIs can be extended. Its storage and networks can be extended. So if we make development based on these, it would be very convenient. Number 3, we support cloud native support multiple clouds to avoid vendor locking. For things like K8s, it is widely accepted by various cloud vendors. So vendors, they can support this standard APIs. Last one is about improvement of efficiency and resources utilization. It's about using the orchestration to improve the efficiency and resource utilization. And this is a Kubernetes architecture. I believe you're all very familiar with this. There is a control plane and data plane. Control plane has master, scheduler, controller, manager, and third-party authentication. And data plane, it has nodes, various nodes. To the right, I've listed some very good design concepts. For example, declarative APIs. You're all very familiar with this, so I will not go into the details. This is a very good design, which is CRD in K8s. It can be used to extend APIs. In Kubernetes, you can define a CRD, and based on this CRD, you can generate development SDK. Through the controller, the APIs can be driven. So you can define a YAML file. You can define a desired state, and there is a reconcile logic in the controller, which can drive this desired state into an actual state. If you have, for example, you have 3 or 5 instances, then Kubernetes can do polling until the actual state is achieved. This can be used in device management. We use it to define the IoT devices so that we can operate these devices from the cloud. This is another one, very good design from Kubernetes. This is a list watch mechanism. If you're familiar with Kubernetes, you'll be familiar with this one. The left-hand side shows the API server connected to etcd. Right-hand side is the K8s client. So I abstract all the things into client, for example, scheduler, controller, Kubernetes, or operator. You can abstract them into a client. And I've drawn some communication principles. Once the client is online, then you can obtain the list. For example, you have Kubernetes. I'm interested in the services and ports running on it. Then I can obtain those from a list. Then based on this list, you can maintain a long connection. For example, you have a port, and you update a label. Then through a watch event, you can send this information to the a client side. So this is the list watch mechanism. But in an edge scenario, there could be some issues. If the network is disconnected for a long time, then a relist will be triggered. This relist will send all the information, including redundant information. So if you have a lot of edge nodes, for example, 5,000 nodes, and 2,000 of them are offline, and they go online at the same time. So there is a relist operation on the data plane, and the system will become unstable. We've done some improvement or refinement concerning this issue. If you're interested in that, you can look into that. These are the key advantages and major challenges. Concerning the key advantages, they are similar to the ones of cloud native. For example, containerized application encapsulation, build once, run anywhere. Second, general abstract definition of applications. This is a de facto standard in the industry. Number 3, loosely coupled architecture. It is easy to be expanded. The API framework is easy to expand. You can use it to define IoT devices. The right-hand side shows major challenges. First one, limited resources. Second, restrict networks. Concerning private network and limited bandwidth and high latency. Last one, offline autonomy needed at edges. The network is unstable and may be offline at any time. So these are the advantages and the disadvantages concerning the platform built on Kubernetes. These are some of our thoughts when we design the platform, whether we should use it to manage edge nodes or edge clusters. The left-hand side is edge clusters. I have master node. The right-hand side shows that I have a controller plane in the cloud, and I have various nodes at the edge. Actually, we had some discussions with Kubernetes, and we conducted a survey. We found that 70% of the users prefer to run edge nodes due to lower cost and easier to be maintained. If the edge cluster is run, then it will consume a lot of resources, and it will be harder to be maintained. Therefore, we chose the right-hand side one. Therefore, our core architecture is about managing edge nodes. But right now, some users, they want to use it to manage edge clusters. So we also did some explorations. This morning, we released a new open source project called Commander. It is a federated cluster. And in future, we'll have some joint exploration with that project concerning how to better leverage the edge clusters. This is the KubeEdge architecture. At the top, it is the cloud, and at the bottom is the edge, and to the right, it is the device side. In the cloud, there is a standard Kubernetes control plane. We didn't do any change to it. You just need to deploy those controllers and etcd. And to the right, there is a cloud call. To address the issue of list watch, we have a cloud call in place. It will check the reliability of the messages. It would refine the repeated data during relist operation. Later, I'll talk more about those components. And there is edge core. We did some integration. We integrated multiple modules so as to save resources. And in edge scenario, it is easier to deploy edge core. We have a tailored Kubernetes called HD. It can be used to manage some container applications. We maintained CSI and CA. And to the right, we packaged some device access capabilities. And there is a mapper. This is what we did to do device connection or access. Mapper would map the data to MQTT. Recently, we developed a SDK for mapper, So you have your device and your own protocol. There are many protocols in IoT. You can have your own protocol and device, and based on SDK, it will be very easy for you to develop a mapper in order to connect your device to the system so that you can manage your IoT device from the cloud. We use a container to deploy mapper.
So this is the architecture of KubeEdge. So those are key concepts of the architecture of KubeEdge, including 5 parts. The first is about open ecosystem. We center on Kubernetes. We don't change control plane of Kubernetes. It means it's 100% compatible with native Kubernetes capability, allowing users to use native Kubernetes API to manage Edge applications. Because many users were concerned about whether it's possible to use Kubernetes API. The answer is yes, because it's the same. And SKTA of Kubernetes can also be used. And besides, we have open list watch APIs at Edge, which is relevant to Kubernetes API. For example, if someone would like to access servers at Edge, they can use this API. We optimize this Edge API as well because we have a Kubernetes that can be accessed to protocols. But now we use Cloud Core and other parts to do optimization. The third is about the Edge device computing protocols, like we define of the protocols with CID. Users could expand based on protocols. We also embed MQTT, Model-Bus, Bluetooth, Wi-Fi, OPC-UA, and ZigBee. You may also define your protocols if you have any. This is to support ecosystem. The next part is about large-scale management of Edge devices. First, we have lightweight components. So there are about 70 MB memory for a whole package. And Kubernetes may occupy 100 MB, so our solution is much lighter. And next one is about pluggable Edge device management framework, and you may deploy the solution with containers. We also support complex Edge cloud network environments. For example, when there is some unstable network at Edge, at application layers, we have a message synchronization mechanisms. It means the message sent to the cloud can be responded by the Edge. So it's a kind of to say, I've already received it, and then there will not repetitive exchange of messages. Otherwise, in today's Kubernetes, and then there could be such a kind of repetitive message exchange. Next one is about application data Edge autonomy. Let's say in Kubernetes, Kubernetes could have their things stored in the application, but once network goes down, or you just reboot the system, what's inside the memory will be gone. In our solution, when there's this connection between applications and Edge, and we cannot really permit such kind of loss of data. That's why we have the Edge database. Applications as well as device have their metadata, which will be stored in database. And once we disconnect networks, and it's time to reconnect again. And before the connection, and data could be read and start up applications. So it means our Edge can run quite steadily. Last but not least, integrated Edge cloud resource scheduling and traffic-based collaboration will have very standard Kubernetes. That's why we can manage both Edge cloud nodes and cloud nodes. For example, we may integrate KubeEdge as well as Kubernetes. Actually, add an cloud, and we may edge traffic at edge and the cloud. Those are the core concepts of KubeEdge. Next, I will dive into KubeEdge architecture, which is cloud core. You see the control plane, including several controllers, which are to get the data from KubeEdge, and then data will be sent to Cloud Hub, which will encapsulate data and verify data. Today, we support MSocket or quick protocols that will be sent to edge protocols. So this is a cloud-based architecture. So this is architecture for edge. We call it edge core process. On the top of it, you see H hub, which will receive the message from Cloud Hub, and it will respond to it once it's received. And the second one is Meta Manager, which is to talk with database. And then next one is kubelet. Once receiving data from kubelet, and the data will be stored in the database in kubelet. And device twin is to support device connection and bus by MQTT, and the data will be sent to devices. On left, you see Q8S operator, which is a new capability. This year, we support operator running at edge. Someone would like to access API servers, for example, CSI, CNI plugins. They have to access edge. That's why we have this operator available, which is compatible with API of Kubernetes. It means you may access your data. If you can get data locally, you can do that. Otherwise, they will ask data from a cloud and get it from a cloud. So now we integrate everything into single one process, which is easy to deploy, and it's also quite light. This is about edge device management process. On the left, you see the CIDs used to define API. Through Kubernetes SDK, you may have some operations. On the right, you see the process graph. Once you set up API, you have to develop a mapper. Once everything are done, you deploy them, and then on the cloud, you may manage devices at the bottom. So from API to device controller, and the message will be sent to the hub, and then the devices, the mapper and devices. Through this process, we can manage devices at edge. This is edge mass of our community. You may have a question about this because in Kubernetes you see kubeproxy or CN, which can help us to realize service discovery and traffic forwarding, while we still need to have this edge match. Because we still believe at edge, we need to have high integration and lightweight applications. We think it's easy to deploy applications. That's why we have this integration. We provide capabilities similar to Kubernetes, like service discovery, traffic forwarding. One thing is quite interesting. At edge, at each node, we have a lightweight DNS server. In this way, we can guarantee once your edge node leaves the network, we can still have service discovery and the pass service. For example, QDS may run at the same location in master, but once the network goes down, and then so the domain cannot be parsed. That's why we need to have a DNS at each node. So those are capabilities of edge mesh. But in the future, we want to add something like ISTO API will be used for service governance, which is very popular today. In the future, we will be compatible with this API. Second one is about cross-domain, sub-network communication. let's say in the connected vehicles, two vehicles need to talk with each other. But their applications cannot talk with each other directly. That's why we want to offer such a gateway to forward traffic between two vehicles. So this is something we're still exploring today. How to deploy clusters and install it if you want to have a sense of what is KubeEdge. Today we have a key domain available in community. With this, you may install it directly. As long as you run this script, run this command, you may just install it, like at Edge. What is get talk? It means when you actually try to connect cloud, you need some credentials through get token. And then you may tag something in the command, and then a certain Edge node will be added. But here I don't have any information about how to install Kubernetes because we're now doing this with standard API. For example, Tide Mini Kuber can also be possible. And besides, at Huawei's cloud or some other cloud vendors, they've already installed Kubernetes. And then KubeEdge can still be added on top of that. Some details about implementation and deployment. For example, KDM init. Through this command, you start. This is the latest version 1.6. So all the logs will be stored. This is about Edge. As I said, join command. This command can help us to add something. I talk about token. Once deploy something, you have to use token to make a record, and then you add that. So it means Edge Cloud will be added automatically, and the credential will be assigned to the node. And then usually this credential or token can only be valid for 1 day. It means you can't really continue to use that after 1 day. Next, I will share with you about what we have implemented in communities. This is a quite typical one. For example, this case uses KubeEdge to manage all of surveillance equipment on the world's longest cross-sea bridge. It's like 30 kilometers long. There are many cameras equipment deployed on the bridge. There are a lot of weathers like snowy, raining weather. And this platform is used to gather all of the data. And this platform can help us to know what's going on the bridge. So our community partner, Xie Technology, has adopted our platform. You see, Kubernetes and Cloud Core have been used. So Cloud Core is to have management over this edge. And besides, we need to deploy those applications and gather data through this platform. There are some applications developed by the user itself, like Mapper, to support a connection with devices. All of the sensor data can be fed into that, and MQTT can help us to make the report. And the data will be reported and further to the cloud. So the cloud will store the data. The sensing data will be stored on the cloud. And then there's also the digital screen, which will monitor everything. Visualization of the data, device management, and other applications. All of this are things they've implemented based on our solution. This is another production case, which is quite interesting. So it's based on Huawei Cloud. This is to manage 100,000 edge nodes on China's highway last year, and China decided to remove the payment of the road toll collection stations near provinces. Whenever you run a car through those tolling stations, you'll be charged. So today, those edge nodes have been deployed at on those stations. So that means all of those tolling part have been integrated into our platform. And with this one, we will know all the applications in our tolling station.
For example, you can do one-click update or upgrade for all the ETC gantries. If there is no such a solution, you need to go to each gantry to do the update. So with this centralized management, the operation and management efficiency is greatly improved. The ETC gantry network connection with the HMRC is very unstable. But with our solution, we can achieve very stable application management. The right-hand side shows some numbers concerning the efficiency improvement. There is 10-fold improvement. We can manage these edge applications remotely from the cloud side. In total, there are 100,000 edge nodes with 500,000 edge container applications. For example, charging, tolling, car plate identification, all kinds of applications. So this is one case study. Later, our community partner will talk about how they implement the solution in their own use case. So after introducing the technologies and case studies, let me talk about the milestones of edge computing in a cloud-native open source community. How the community was developed. At the very beginning, in 2018, in Kubernetes community, the IoT Edge working group was established. This was established by Huawei and the open source community, and then in November 2018, Huawei open sourced KubeEdge. This is the first cloud-native open source project, and in March 2019, KubeEdge became the first official edge computing project for CNCF. In June 2019, we released version 1.0, and in 2020 and onwards, we had very fast development. Other companies also came up with cloud-native edge computing. In September 2020, we promoted our projects from sandbox project to a more incubating project. As I said earlier, in September 2020, our project was promoted to an incubating hosted project of CNCF. There are many developers and contributors in this community, and we also have a lot of contributing organizations. The right-hand side shows the ecosystem. We have SIG, focusing on three directions. One is device IoT. This is used for device management. Second, SIG AI. This is for edge AI. For example, when it comes to intelligent driving, edge AI is very important. And we have a sub-project, Setna. This is used to address the edge cloud synergy AI issues. Next speaker will talk about how Setna was used to address the edge AI issues. Number 3, SIG MEC. This is for 5G access. So these are the 3 SIGs. If you are interested in them, you can follow us. We have regular community meetings. You're welcome to join our regular meetings. Community version release pace. We made a major release every 3 months. Latest version is 1.6, and in 3 months we'll have 1.7. Between 1.6 and 1.7, we would release some minor versions to fix bugs. And we support both x86 and ARM, because at the edge there are both ARM servers and x86 servers. So we support both of them. These are the community partners and users. I have not listed all of them. As you can see from the slide, there are so many partners and users. The right-hand side shows various application scenarios. Future prospects. Concerning infrastructure, in future, we will make some exploration on the edge clusters. Concerning platform capability, edge cloud traffic collaboration and maintainability, observability, and serverless design. This will be our focused fields. And business domain, for things like internet, IoT devices, and AI edge cloud synergy, and MEC, primarily on access. Lastly, concerning community operation, we're now running an incubating project in CNCF. We welcome all of you to join our community. We'll add new maintainers. Maintainers will be involved in code check, code review, and code checking. And we'll have joint promotion with partners and community case sharing concerning how people are using those projects and implementing those projects. So that's all from me today. Let me do a recap concerning KubeEdge. This is a CNCF incubating project. We have open community governance, which allows the users to participate in community development and governance. For example, the version planning and the development of versions are all planned by the community participants. And we support the dynamic device access. We are compatible with Edge Cloud Synergy. We extend the cloud capabilities such as AI collaboration, data collaboration, application collaboration, and management collaboration to the edge. And cloud edge communications, this is about high-speed, reliable, and secure communications between cloud and edge. And easy maintenance is achieved by lightweight and plugin-based edge framework. And lastly, we support heterogeneous hardware. We support all kinds of hardwares. There's a decoupling from the hardware so that we can support all kinds of hardwares in the scenario of edge computing. That's all from me today. This is our GitHub address. This is the Slack address. There are many developers. in that community. We have the Huawei maintained public account. You can scan the QR code to follow our public accounts concerning the container magic cube. And you can also scan the code to the right-hand side to join the group, the WeChat group. Lastly, this is our training camp concerning the training on cloud native. You can scan this code to follow our training camp. We have lots of experts delivering the trainings. That's all. Thank you. You can scan the code to appraise the course.